Now let's go through an example of polynomial fitting. So how do we find a function defining a sequence if it's not arithmetic or geometric? Well, one way we can do that is we can see if it can be done with, be approximated with a polynomial. So let's look at the sequence 1, 5, 14, 30, 55. So we can see it's not arithmetic because it's not a common difference. We can see it's not geometric because there's not a common ratio. But let's go ahead and find the difference between the first few terms, and that's going to give us a new sequence. So 5 minus 1 gives me 4, 14 minus 5 gives me 9, 30 minus 14 gives me 16, and 55 minus 30 gives me 25. So here's my new sequence. Now let's find the difference between the terms in this sequence. 9 minus 4 is 5. 16 minus 9 is 7. 25 minus 16 is 9. Okay, still nothing very exciting. But what if we do this step again? That means 7 minus 5 gives me 2. 9 minus 7 gives me 2. Now I have a constant term, and there's a constant difference between each of my terms. If I come across a sequence, and it will be a degree k polynomial if and only if the sequence is delta k constant. So the kth sequence differences is constant. So in this case, it wasn't the first, it wasn't the second, but it was the third. So we could approximate this with a degree 3 polynomial. So let's take a look and determine whether or not this can be described by a polynomial, and if so, what degree it would be. So I take 4 minus 1, which is 3, 9 minus 4, which is 5, 16 minus 9, which is 7. Next I take 5 minus 3, which is 2, and 5 minus 7, which is 2. So this would be a degree 2 polynomial. Next I have 1, 2, 4, 6, 16. Well, we can see that this is, it's supposed to be this. 1, 2, 4, 8, 16. We can see that this is geometric, right? Every time that this isn't geometric, that this is 2 to the n. And so because of this fact, we don't want to, it grows faster than any polynomial, so we don't want to define it with a polynomial. Next, let's look at 0, 50, 183, 484, 1055. So my first difference is 7, 43, 133, 44 minus 183 is, 484 minus 183 is 301. Our next difference, 571. So let's try this again. 43 minus 7 is 36. 133 minus 43 is 90. 301 minus 133 is 168. And 571 minus 168 is 403. Okay, we got to keep going. Next, I'm going to get 54, 78, 102. So now I'm on my third difference, right? This will be delta 3. Let's try one more time. I get 78 minus 54 is 24. 102 minus 78 is 24. So here I have, this would be a degree 4 polynomial. All right, here I have the Fibonacci sequence. So let's see if this could be approximated with a polynomial. So the difference between this is 0, 1, 1, 2, 3, 5. Again, 1, 0, 1, 2, sorry, 2, yep. And then 1, 0, 1. See, this is just going to keep repeating and repeating, so there's no polynomial that can define the Fibonacci sequence. So let's find the polynomial for this sequence. So the first thing I need to do is figure out what degree polynomial is going to be. So the difference here is 2, 4, 6, 8. The difference between all of these is 2. That's when I get to my constant. So this is going to be a degree 2 polynomial. So I know I have something of the form a sub n, where an squared plus bn plus c. So I know that a sub 0 is 2. Sorry, a sub 0 is 0, and that makes sense. So let's take a look at a sub 1. Sorry, a sub 0. So this would mean a n squared plus bn squared plus c is going to be 0. So this means I know that these terms, a0 squared plus b0 plus c, I know my constant's going to be 0. So now I have a sub 1 is 2. So that's going to be a times 1 squared plus b times 1. So I get a plus b equals 2. So that means a and b are both 1. So I've solved my equation. My formula is a sub n equals n squared plus n. Let's make sure this works. Let's do a sub 3, which is 6 right here. That's going to be 2 squared. Sorry, that's going to be 12. It's going to be 3 squared plus 3. Well, 9 plus 3 is 12. Awesome. So we fit a polynomial to our sequence.